Alright, this time we're going to talk about a noble gas configuration instead of just the actual full electron. This one's typically most people's favorite, but a little bit confusing to start with. So, noble gases are special in that their outermost s and p orbitals are filled. Now, we'll eventually talk about that s and p orbitals are typically what we call our valence electrons, meaning noble gases have all their valence electrons filled to the level that they want them to be filled. Now, the one exception is helium, and that's mainly because helium's electron configuration is 1s2. Now, this is filled. It has its whole first energy level filled. It just doesn't have any p. So, for everything but helium, all the s and p's are filled. So, they serve as very useful checkpoints on the periodic table, as that means that any element after a noble gas is simply just adding electrons on top of the noble gas's configuration. It's basically noble gas plus 3 or 4 electrons. So, that's the basis for this type of configuration. The noble gas electron configuration, which is sometimes called the condensed configuration, is basically a shorter version of the full electron configuration. Instead of writing the whole thing out, we write, well, a lot less. That's why this is kind of most people's favorite. We use the noble gases as checkpoints and only write any electrons that are past the most recent noble gas. So I said that every element is basically some noble gas plus a few electrons. Well, we only write basically those few electrons. Well, and the noble gas, but we don't bother with wasting our time writing out every electron. We just write those that we really need. So in a noble gas configuration, the most recent noble gases configuration is represented by the gas's symbol written in brackets. For example, helium or krypton. This is referred to as the noble gas core, or more commonly, our core electrons. Now, sometimes core electrons are a little bit more, but basically, when we have a noble gas plus more, these are the ones that will likely not be bonding. These are the ones that are going to be staying. These are, again, our core electrons. Any electron written after the core electrons are called our outer shell electrons. Now, some of those will involve d electrons or f electrons in addition to maybe a p or something. And really what our outer shell electrons are, those are the electrons in the outer energy level, so the highest energy level. But basically all the outer shell electrons will be the ones that are not the core electrons. So these outer shell electrons include our valence electrons. There may be more, but our valence electrons are always going to be written after the noble gas. And then the electrons that we write after our core electrons as being in s or p blocks specifically, those are called our valence electrons. So, there you go. Valence electrons are in s or p, and they're the highest energy level of s and p blocks. For a noble gas configuration, use the following steps. First off, you got to determine the most recent noble gas. Basically, find your atomic number, and then find the noble gas with the highest number that is still less than your atomic number. So, just basically start counting down and find the most recent noble gas. Or find the row that your element is in and go up a row and all the way to the right. That'll be your most recent noble gas. Secondly, subtract that noble gas's atomic number from the total electrons that you have to place. So, let's say your atomic number is 14 and the most recent is 10. That means that you've only got 4 extra electrons you got to place. The other 10 are considered our core electrons and will be represented by, again, the noble gases symbol in brackets. We only care, we're mainly going to be writing out those 4. Okay, then step 3, write that most recent noble gases symbol in brackets. So again, that'll look like neon or krypton. So a lot of people tend to skip this step, but when you do, you're skipping out on your core electrons. You're skipping out on the main base of your foundation. So you have to write this part. This is, most of your electrons are represented by this. And then 4. Start placing your electrons after the noble gas, but again, still according to our arrows chart. So typically, you're going to be starting in the S block. That's after the noble gases rows P block. So if the noble gas is in row 5, you're starting after 5P, which would be 6S. Or if your noble gas is in row 4, then you're starting after 4P, which would be 5S. So you'll get the hang of this pretty quickly. So, noble gas configuration of a tungsten, which is W, atom. Take a few minutes, try this, and try the next example. And then I'll show you how to do this one and give you the answer to the second. Come back in a bit. Alright, welcome back. Tungsten is element 74. And the most recent one is xenon with 54. So, 74 minus 54 is 20. That means we only have 20 outer shell electrons to place. But we have to start by putting our core, which is xenon. Xenon is in row 5. That means we're starting after 5p, which means we're starting at 6s. Okay? But again, we're only placing 20. So that's 6s2, 4f14, 5d4. That's your answer. So again, start after the most recent noble gas. It was in row 5, so you start in 6s. You also can start, another way to look at it is we're starting in whatever row W is in, because W is in 6. But that gets a little annoying when you're dealing with F or D elements, like tungsten, or F or, technically, D. Because notice it ends in 5D, even though tungsten technically is in the 6th row. So it's easier just to go off the noble gases, at least in my opinion. If you're fine with a different way, do what you wish. Alright, lastly, uranium. Again, hopefully you have time to try this. If not, go and pause this, and then because I'm about to show you the answer. Alright, here's uranium's noble gas configuration. There you go, that's uranium. Well, as always, thanks for watching.